So here we have a question of gate physics that requires the understanding of special theory of relativity. So it goes something like this. Two spaceships A and B, each of the same rest length L, are moving in the same direction with speeds 4c by 5 and 3c by 5 respectively, where c is the speed of light. As measured by B, the time taken by A to completely overtake B is how much? Now, this question requires an understanding of special theory of relativity and, more importantly, an understanding of velocity transformations and length contraction. You see, in our day-to-day life, when two objects are moving and we want to find the relative velocity between them, then the transformation is very simple. If there are two objects moving in the same direction, let's suppose one car is moving at 200 kilometers per hour and another car is moving at 100 kilometers per hour, then with respect to the second car, the first car has a velocity of 200 minus 100 is equal to 100 kilometers per hour. Very simple. So this is a very simple velocity addition theorem that is applicable in our day-to-day life, in our day-to-day velocities that we experience. However, in relativity, when we talk of objects that are moving at very, very high speeds comparable to that of the speed of light, and this very simple velocity addition theorem does not work. In fact, we need a new velocity transformation equation which is consistent with the postulates of special theory of relativity, and that is something that I have obtained in one of my previous lectures. So we are going to make use of that very simple velocity transformation equation in this particular problem. So this is how it goes. So if we have two frames of reference, let's suppose that this is S frame of reference and this is S dash frame of reference, and the S dash frame of reference is moving with a velocity of v with respect to the S frame of reference along the x dash axis. In that situation, if there are two observers in both these two frames of reference and both of them are trying to measure the velocity of some external object, let's suppose that we are only interested in the velocity components in the x-axis, then according to the first observer, let's suppose the velocity component of this object along the x-axis is ux, right? And according to the second observer, who is in relative motion with respect to the first observer, by the way, the velocity component of this object along the x dash axis is given by ux dash, then relativity tells us, or relativistic velocity transformation gives us, a relationship between these two velocities or velocity components along the x and the x dash axis respectively, and this goes something like this. So this is ux dash is equal to ux minus v upon 1 minus ux v upon c square. Now this is a very standard formula for the relativistic velocity transformation that we can use in our scenario. So here we have two spaceships that are traveling in the same direction. We can consider this to be the x-axis with different velocities. At one point in time, the second spaceship is just behind, or rather the spaceship A is just behind the spaceship B, and after a certain time interval, the spaceship A has just crossed the spaceship B, or rather the end point of spaceship A has just crossed the front end of spaceship B. So we are interested in finding out what is the time period between T2 and T1. So what is T2 minus T1? So how much time does the spaceship A take to overtake spaceship B? And to do that, because we are interested, as the question says, how much time with respect to spaceship B, so we are making measurements with respect to an observer on top of spaceship B. So with respect to an observer who is moving with the spaceship B, I want to measure the time period it takes for A to overtake B completely. So for that, I'm going to use this velocity transformation. So what I'm going to assume is that, let's suppose this S frame of reference is the Earth frame of reference. All right. If this is the Earth or the ground or the lab frame of reference, then with respect to Earth, both the spaceship A and B has velocities as given here. And let's suppose the S dash frame of reference is spaceship B, all right, and this object is spaceship A. Okay, So what is the speed of A with respect to the earth? It's already given to us. That is 4c upon 5. So we have ux is equal to 4c upon 5. What is the velocity of B with respect to the earth? Already given to us. That is 3c upon 5. So the velocity of B, which is the second frame of reference with respect to earth or a ground frame of reference, is V, which is given to us as 3c by 5. And ux is the velocity of A with respect to earth. Now we are interested in finding out what is the velocity of A with respect to B, and that comes from ux dash. So I'm going to substitute these values here. If I do that, I simply get 4c upon 5 minus V is 3c upon 5, and we end up getting 1 minus ux is 4c upon 5 multiplied by 3c upon 5 into 1 upon c square. The c gets cancelled with the c square, and we are left with, basically, in the numerator we have 4c upon 5 minus 3c upon 5, that is c upon 5 in the numerator, multiplied by, in the denominator we have 5 into 5, 25. So 25 minus 4 into 3, 12, and you have 25 at the top. So this simply leads to 5 and the 25, we are left with 5 in the numerator. So 5c upon 25 minus 12 is 13. So we have here the speed of A with respect to an observer in B is 5c upon 13, which is not a simple subtraction of 4c by 5 minus 3c by 5. So this is the speed of A with respect to B. So now we want to calculate how much time it requires for A to overtake B. So if you look here, if A wants to overtake B, it needs to overtake the length of B, but it also needs to overtake the length of A. Alright, so the front end needs to overtake the back end and reach the front end of B, but the length of A must also go beyond it. So in a sense, the length of B plus the length of A is the distance that needs to be overtaken, but we are making measurements with respect to an observer in B. That means for an observer in B, the length of the spaceship B is already given to us, right? The length of the spaceship B, the question tells us, is its rest length. So the length of the spaceship as measured by an observer at rest with respect to that spaceship is given as L. However, what is the length of spaceship A with respect to the spaceship B? It's not the same as L, but rather it's something else. It's the contracted length. We are going to call it L dash. You see, when you measure the length of an object at rest, you measure its rest length. But if the object starts moving at very high velocities and then you measure its length, you measure the contracted length, which is simply given to us by length contraction, which says that the length measured of the object which is in motion is equal to the rest length L multiplied by root over 1 minus the speed of the object with respect to the observer, which is 5c upon 13 whole square upon c square. So the length of A and the rest length of A is the same as the rest length of B, but for this observer who is making the measurements, the length of A is this much, the length of B is L. Okay, so let's calculate what is the length of A. This gives us L root over, so 13 square, so c square and c square gets cancelled. We have 169 here and 169 minus 25 here. So this gives us 169 minus 25 is 144. Root over 144 is 12 and root over 169 is 13 L. So as you can see, the length of A comes out to be L dash as measured by this observer, and the length of B as measured by the same observer is L. So if I am interested in calculating the time it takes for the spaceship A to completely overtake the spaceship B, then I must add the length of B plus the length of A according to this observer. So the time taken is nothing but distance divided by the speed, right? So what is the distance? Distance is the length of B, which is L, plus the length of A as measured by the observer, which is L dash, divided by the speed, which is the relativistic speed 5c upon 13. So now if I perform the calculations, then my answer should come out to be L plus 12 upon 13 L upon 5c upon 13. So this is equal to 13 plus 12 is 25 upon 13L multiplied by 5c upon 13. The 13 and the 13 gets cancelled. 5, 25, we have 5 in the numerator and we are left with 5L upon c. So in units of L upon c, 5 units is the time period it takes for the spaceship A to completely overtake the spaceship B with respect to an observer in spaceship B. That's it. That is a gate physics question we have solved using length contraction and velocity transformations. Thank you very much. I'll see you in the next one.